Very good evening, everyone, and welcome to the Amateur Radio Technician class. This is session number 6. Certainly a special welcome to the new participants to the class. We are getting a couple persons joining each week, and we certainly welcome you. Just a note in terms of the Zoom platform, we'd like to advise each person to consider updating your Zoom software, whether you're using Zoom on your computer, tablet, or phone. Just make sure that you're using the latest version, as the latest versions contain security updates as well as feature enhancements. Let's see where we are in terms of our progress going through the curriculum. We are on the third bullet point, radio wave characteristics. So we are making good and steady progress through the curriculum. And I congratulate you for going through thus far and sticking to it. Last class, we looked at the transformer. We looked at what is a rectifier diode. We looked at tune circuit, antenna, relay, what a meter is. We looked at the integrated circuit, a voltage regulator, shielded wire, and what's an electromagnetic wave. So just a couple of questions in relation to last class. So alternating current and direct current, what does that look like if you were to graph it? So on the left-hand side of your screen, you would be seeing what looks like a up and down wave. It's called a sinusoidal wave. And it's varying in polarity. It's positive, increasing to a peak, and then decreasing to 0, and then going negative to a negative peak, increasing until it goes through 0 again, and so on. So one of these is considered one cycle, okay? So that's alternating current, where the voltage increases positively, then decreases to 0 and goes negative. So notice it is varying. Alternating current is alternating. Direct current, on the other hand, if we were to graph the direct current, notice it stays positive. This is the positive direction of the graph. And it's steady, a straight line. So it's not alternating, it's not going negative, it's not going below the 0 line and coming back up as the alternating current. So that visually gives us a representation of the difference between alternating current and direct current. Last class, we looked at the function of a diode, in particular in an electric circuit called a power supply. So just thought I'll throw in a little further explanation so that you can see what a diode does to alternating current. We saw that the circuit had a diode in it. We applied an alternating current, which is this sinusoidal wave that we're seeing here. When it passes through a diode, remember a diode, we use the analogy of a check valve in the water circuit, where a check valve will allow water to go in one direction only, but if the water tries to go in the opposite direction, it will stop it. And we give an example that a check valve is very useful for your water tank, because you want water from water line to go into your water tank. But if there's no water in the water line, you do not want that water in your water tank to go back into the water line. So you employ a check valve. So a diode is the electronic equivalent of that check valve. It allows flow of current in one direction. But what happens when we apply an alternating current to a diode? It comes out on the other end, and notice, right? This is considered pulsing DC, right? You know, you only get in the positive side of the cycle, or rather one side of the cycle. You notice it's going here and then clipping. You get nothing, and then it goes up here again and it clips. So notice the bottom part of the cycle here is missing when it passes through the diode, because the current is only allowed to go in one direction. So only when it's on the positive stroke, it allows the current through. But when it tries to go negative, it says, you cannot go back. You can only go forward through me. So this is how it looks visually when we say that a diode takes, in the case of a rectifier diode in a power supply, it takes the alternating current and converts it into pulsing DC. Also, this is the entire power supply circuit in block form that we saw last class. We saw the actual electronic circuit, the circuit diagram or the schematic. This here is just a block diagram of those components. It doesn't have the individual components in terms of the symbols, but it has a block diagram showing you, well, you have an alternating current, remember the rectifier diode, remember the filter capacitor, and so on. So it is a block diagram showing you the components represented. And this is just the graph to give you an idea as to what happens in the power supply circuit that we saw last class. This is your alternating current supply coming from your mains, sinusoidal waveform, positive, negative, and so on. And when it goes through your rectifier diode, this is what happens. Pulse, 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 right? Rectifier diode can in fact have both sides of the pulses if you use a bridge rectifier. So what you're seeing here is the result of a bridge rectifier where it's rectifying both of the cycles. So don't get too confused. You know, the previous one you saw, it stopped here, went flat and came up. This is a bridge rectifier, and that's why we're getting the full cycle pulse DC. But the important thing is that when it comes through the rectifier as pulse DC, it goes through the filter capacitor, what we saw in the last circuit, and it smoothens it, right? So notice it's not pulsing as vigorously as before. It's just, you know, a light wave. When it comes out there, that is what you go to the DC output. And if we apply something called a voltage regulator that we looked at in the last class, notice it regulates the voltage to a very smooth DC. So this is what a DC power supply does. It takes the alternating current from your mains when you plug it into the wall, and it delivers a direct current which you use for your radio equipment, because your radio equipment is typically 13.8 volts DC, whereas your mains is 120 volts AC. Also, this diagram here shows you how a transformer is constructed. So we got some questions from persons, you know, this transformer that we're talking about, how does it work? Well, a transformer is consisting of two coils, at least two coils, around a magnetic core. And one side is called the primary, where you apply your alternating current. And then the other side, which is your output, is the secondary, where you have an output of alternating current. And the relationship between the input alternating current and the output alternating current is a ratio of the number of turns of these coils, all right? So if we see here, we have a transformer where we have 120 volts in, but because we have a ratio where you have 2,500 turns to 500 turns, right? A ratio of 5 to 1, notice that the output voltage is 1/5, 24 volts, compared to the input of 120 volts. And just some points to note about transformers, a little further information than we would have discussed. Transformer can be used to convert alternating current from one voltage to another. Notice it must be alternating current. It cannot convert direct current. The voltage is either stepped up or stepped down. We did note last class that you can actually have a transformer where the voltage output is the same as the input, all right? Sometimes they call that an isolating transformer. There are no moving parts, right? It's just coils of wire around a metallic former, or called a magnetic core. It works on the principle of magnetic induction. So if we were to go back to the previous slide, when you apply an alternating current to this coil, a magnetic field develops. But because this is a iron core or magnetic core, laminated iron, the magnetism develops here, and because it's alternating current, the magnetic lines of flux increase and then decrease. So it increases and then it falls. It increases and then it falls. And those magnetic lines of flux, when it cuts this other wire here, induces a current flow in this secondary coil of wire. So that's how a transformer works. Because of the alternating current that is flowing here, it induces a magnetic field and that magnetic field induces a current flow in the secondary coil. So it's not magic, it's magnetic. It's constructed of 2 coils of insulated wire on a laminated steel core. The transformer, voltage is applied to 1 coil called the primary. The iron core becomes magnetized, which is what we just said. The magnetic field changes continually in polarity and intensity, and then a voltage is then induced by the magnetic field in the other coil called the secondary and causes a current to flow. We promised you that we will show some of the, well, we saw the symbols for the various electronic components, but we also said we will give you an idea what it actually looks like in practice. So this is the symbol for a transformer. This is an example of what a transformer looks like. Notice we have the 2 wires coming into the primary and we have 2 wires leaving the secondary. So this is like the input voltage and this is the output voltage. You might input the mains current here, the AC from your mains, 120 volts AC, and then the output, maybe you might have something like 14 volts DC or 24 volts DC or some other output. Sorry, AC, my apologies. Let me restate that. So 120 volts AC input, and you will have 12 volts AC or 14 volts AC or 24 volts AC. It depends on the number of turns on your application. So remember, a transformer takes AC and converts it to AC, all right? This is what an antenna looks like. One example of an antenna, and this, you recall, is the symbol for antenna. All right, so this is the symbol for a relay. And remember, we said a relay, you can apply 1 signal and control many signals. So you can switch several other outputs by 1 control signal. And this is how a relay could be constructed. Notice a coil here. When you apply a voltage to the 2 control pins, this is magnetized and these pins are pulled in this direction and contact is made with some pins. When you release the power, then this releases and goes back to the other pin. So that's why we can say it switches, but notice that you can switch multiple circuits, right? So Kaz, thanks very much for pointing that out. It's not necessarily 1 circuit, as in the case of this relay here. You can actually have multiple switching. So you just replicate this part of the relay so you can see how many circuits that you're switching. But the symbol does show that we are switching 1 circuit. This is how it's constructed in practice. All right, so for example, you could have a 12 volt DC supply to the relay, and you are controlling 120 volts AC on these pins. So you can apply a 12 volt battery supply here, and you can turn on some lights in your house on these pins, or you could turn on a motor. Of course, the larger the current flow, you will need a larger relay. We talked about a meter. This is an example of a voltmeter. So it shows voltage. If we apply this to your mains, you will see 120 volts. So the needle will come somewhere here. So remember, a meter is a visual indication of an electrical property. We also talked last class about what an integrated circuit is. Remember, we said it consists of dozens, hundreds, thousands, millions even of individual components that's put onto 1 silicon wafer and packaged. So this is an example of what an integrated circuit looks like. Sometimes people call it a chip. This is an example of what a voltage regulator looks like in practice. Some example of what fuses look like. You may have come across these fuses, you know, if you have ever had to change a fuse before in a device. Some of you may be familiar with this type of fuse. This is commonly found in the automotive world or in cars, right? Split type fuse, right? Right, so shielded wire. Shielded wire, notice that you have the outer jacket of the wire or the cable, and then you have the individual wires that's insulated, some of them. Sorry about that. But notice here, there's a foil around the wire, right? This foil here shields the wire, all right? So when we talk about shielded wire, it's foil or some braid of metal around that is shielding it from interference and so on, all right? So this is shielded wire. Now we're going to go through a couple slides here before we get into the no-nonsense guide material. These slides here should help us understand some of the things that we will be looking at in that material. The first thing that we want to look at is frequency bands and wavelength. So for our amateur radio exam, we need to know what is HF, high frequency. We need to know what is VHF, very high frequency, and we need to know what is UHF. So you may have already heard, you know, channel 13 on the VHF band of your TV, or channel 6 on the VHF band of your TV, or channel 16 or channel 18 on the UHF band of your TV. So you should probably already be familiar with the concept of VHF and UHF. But what does it mean when we say something is in the UHF band, and what does it mean when we say it's in the VHF band? And also, what does it mean when we say something is in the HF band? So as amateur radio operators, we talk about that all the time. We say we have an HF radio, or someone is on the HF band. Well, HF simply means high frequency, but what does it mean to be high frequency, as opposed to very high frequency, as opposed to ultra high frequency? What does it mean? Well, quite simply, when we talk about frequency, think of the number 3. Right? That is the magic number, the number 3. So the HF band is from 3 megahertz to 30 megahertz. That is all that it means when we say we are on the HF band, or we in the HF spectrum, or we on HF, right? VHF, on the other hand, is from 30 megahertz to 300 megahertz. Right, so remember I said, remember the number 3? Yes. And UHF is from, well, you probably get the pattern already, 300 megahertz to now 3000 megahertz, or 3 gigahertz. So this is where our units come in, the prefixes that we learned a couple classes ago, to go from megahertz to gigahertz, right? So notice on the slide, they didn't tell us 3000 megahertz, they said 3 gigahertz. But we know from our prefixes that 3 gigahertz is the same as 3000 megahertz. So look at the pattern here. 3 to 30 megahertz, 30 to 300 megahertz, 300 megahertz to 3000 megahertz, or 3 gigahertz. So that is how the HF, VHF, and UHF goes. If we look at this diagram, which is a little more expanded, it gives you a lot of information. It tells us the VHF part of the spectrum, the UHF part of the spectrum, and the HF part of the spectrum. But it also tells us about all the other parts of the spectrum that we will not really be discussing in detail, but we've provided information for your interest. Notice here that there's very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, and so on, super high frequency, right? Notice we also have something here that shows what those frequencies are. 3 kilohertz, 30 kilohertz, 300 kilohertz, 3 megahertz, 30 megahertz, 300 megahertz, 3 gigahertz, 30 gigahertz, and so on. So notice the number magic 3, right? This is how they determine the various bands. What is HF, what is VHF, what is UHF. So as we said before, HF is between 3 megahertz and 30 megahertz. We said VHF is between 30 megahertz and 300 megahertz. And UHF is between 300 megahertz and 3000 megahertz, or 3 gigahertz. But notice we also, apart from saying HF, VHF, UHF, and we also saying 3 megahertz to 30 megahertz. Notice here, they have some lengths. And remember we talked about wavelength. So we're also seeing the wavelength associated with these frequencies. So apart from saying HF is from 3 megahertz to 30 megahertz, we're seeing it's from 100 meters to 10 meters. And that length is the wavelength, right? There's a relationship between frequency and wavelength that we'll come to in the class in a bit. But I've just reproduced that formula here, where the frequency is equal to 300 over the wavelength. And if you move the terms around, you'll get wavelength is equal to 300 over the frequency. We will come to the use of that formula in a little bit, but it is here for you to learn that relationship between frequency and wavelength. We say it's an inverse relationship. So this should give us an idea. Just to mention, the various bands, they show us the things that operate in these bands. So we don't really need to talk about medium frequency, but notice AM radio is inside of the medium frequency part of the spectrum. Notice that your FM radio is in the VHF part of the spectrum, right? And 95.1 FM is 95.1 megahertz. So notice 95.1 megahertz is somewhere here, right? It's more than 30 megahertz and it's less than 300. So because it's 95.1 megahertz, it's in the VHF part of the spectrum, all right? Notice that because UHF is between 300 and 3 gigahertz, Wi-Fi signals and so on, UHF television is in this part of the spectrum. So this will hopefully give us a visual idea as to when we come to talking about HF, VHF, and UHF, the relationship. You may want to come back to this slide from time to time. Also, another slide that I wanted to show you before we get into the material is when a radio transmits a signal, we talk about line of sight, but radio line of sight, because there's the curvature of the earth, radio signals will not travel exactly like how light will travel as a straight line. Radio signals will curve a little bit, or we say it will refract a little bit. So notice that if I'm standing here on the Earth's surface, this may be Trinidad, and maybe this here is Puerto Rico, right? If I'm transmitting a signal, this signal may go straight this way, but because of the curvature of the Earth, it goes a longer distance. So please note that when we talk radio and we talk line of sight, there's optical line of sight, and then there's the radio horizon, right? So note that radio signals, even though we talk about it goes at the speed of light and it works like light, the radio signal actually hugs the Earth a little bit more, a little bit longer, and travels a little bit longer. The other thing about radio signals is that VHF and UHF signals, when it transmits from the surface of the Earth, it goes up, right? You have two waves, you have the ground wave and you have the sky wave. The sky wave will go straight through the ionosphere of the Earth, but HF signals will go and bounce off the ionosphere. This is important. So you may wonder why hams say, you know, we can communicate without cellular tower infrastructure from one part of the continent or one part of the world to the other. It is because that HF signals can bounce off of something that's called the ionosphere. The signal will leave your transmitter, go into the ionosphere, bounce and drop to another part of the Earth, covering a very large distance. Not does it only bounce once, it can bounce many times. Sometimes that is referred to as skip. The signal is skipping, but it's skipping off of the ionosphere. And in another slide, we'll see where the ionosphere is or what the ionosphere is. But just bear in mind that HF signals bounce off of the ionosphere, whereas VHF and UHF signals typically will pass through the ionosphere and go straight out into space. Need to know the difference between the properties of HF frequencies and VHF and UHF frequencies. Knowing that will let you know how to use them and when to use them. So we talked about the ionosphere before. So this is an Earth diagram here. We see the map, Africa, Asia, and so on. So this is the Earth. And notice above the Earth, we have the ionosphere. But let's look at the diagram on the left-hand side. This is the surface of the Earth at the bottom here. Notice the water. Well, as we go up on from the surface of the Earth and we go above, up to 10 kilometers, we have the troposphere. Note that term, troposphere, because we'll come to that term a little bit when we talk about tropospheric ducting. All right, so note where the troposphere is. Then we go up to the stratosphere, right? That is all the way 10 kilometers to maybe about 50 kilometers. All right, then we have the mesosphere, and then we have the thermosphere. But notice we are seeing ionosphere D layer, ionosphere E layer, and ionosphere F layer. All these layers, the ionospheric layers, HF signals will go and bounce and come back down to the Earth. And these ionosphere layers don't all exist at the same time. Sometimes they exist and sometimes they don't, based on the sun. The sun's rays, the energy from the sun can create the ionosphere layer or change how high they are or how thick they are or where they exist, right? That's what this part of the diagram is showing. that when the sun is out against the Earth's surface, notice the different layers. We have the E layer and the F layer existing, right? And you see E layer and even a D layer. And we have the F layers in two regions, F1 and F2. But notice in the night, when there's no sun hitting, there's no D layer, and we see an E layer, and we see only one thin F layer. So that should tell us that during the daytime, when the sun is out, the ionosphere changes. And that is important, amateurs, because we need to know during the daytime what frequency will go and bounce off the ionosphere and what frequency will not, right? What we call the maximum usable frequency. And notice during the daytime, it's different to the nighttime. Also, we need to be aware of the difference between simplex and repeater operation. So those of us who already use radio, we know sometimes we can talk from one radio to another radio direct on a frequency, one frequency, but we know that is short range. We call that simplex transmission, where you use same frequency and you go radio to radio, short range. Those of us who use radio note that if we use a repeater tower that's located on a hill, let's say in the Central Range or on Cumberland Hill, that we can be one part of the country and use a radio and talk to somebody in another part of the country. That is because the radio is using two frequencies. It goes to the repeater via one frequency and transmits via another frequency wide area and can talk to persons at a longer or larger coverage area or a greater distance than you would be able to radio to radio. So just bear in mind that a repeater allows you to talk much larger distances than you can with just one radio to another radio direct. Sometimes we call that simplex operation on one frequency direct. And when we go through a repeater, we call that repeater operations that use two frequencies. Another term that we'll come across shortly when we go into the material is knife edge diffraction. So if you are transmitting from one location and you are trying to get your signal to another location, notice that line of sight isn't possible, right? The signal will not be able to have a line of sight from the transmitter to the receiver. However, sometimes when you have very sharp edges or sharp objects like this peak of a hill and this other peak of a hill, the signal itself can be diffracted on these very sharp edges, and the signal goes this way. And when it comes here to this other very sharp edge, your signal can diffract and reach here. So while line of sight is not possible through a special property called knife edge diffraction, radio signals can seemingly go places that you don't think it would or it not ought to go. And that property is called knife edge diffraction. So we should be taking a break very shortly before we go into the material. So let's do that now. Let's take a 2-minute break and we will come back and go straight into the no nonsense guide. So please take a stretch, have a bathroom break, have a drink of water, and we see you in a couple of minutes. Okay, so welcome back, everyone. Let's go straight into the material. Last class, we said that radio waves travel at the speed of light. Welcome back, everyone. Let's go straight into the material. Last class, we said that... And I apologize for the echo. Right. So the speed of light, 300 million meters per second. That's the speed of light. But when we are doing calculations, it will be easy for us to just divide everything by 1 million to make the numbers a little easier, right? That's the point that they're making here. So when we're doing calculations, remember that formula that we saw a little earlier, where we said that wavelength is equal to 300 over the frequency. And vice versa, frequency is equal to 300 over the wavelength. You just move the two terms around. But instead of using wavelengths in millions of hertz, we will just use megahertz. And instead of using the speed of light as 300 million, we will just use 300. Basically, we have divided everything by the frequency, sorry, we divide it by a million. So we use megahertz for the frequency and meters for the wavelength, and we use 300 instead of 300 million. We just divided everything by 1 million to make it easier. That's the point that they're making here. So this is the formula that we need to learn, that the wavelength in meters is equal to 300 over the frequency in megahertz. That is the formula that we must learn, that was presented a little earlier on a slide. So let's continue. So they tell us the converse of the equation is that the frequency in megahertz is equal to 300 over the wavelength in meters. That's what that representation means here. So we can use that to calculate. If we have the wavelength, we can find out the frequency. If we have the frequency, we can find out the wavelength using this formula. Again, you should be seeing a pattern in respect of when we did the Ohm's law formula last time with the power formula. Once we have two of the terms, we can calculate the third one. And one of the terms is a fixed number or a constant really, which is 300. So let's go straight into, before we go into the questions, they make another point here. Because of this inverse relationship, the lower the frequency, the longer the wavelength, and vice versa, meaning that the higher the frequency, the shorter the wavelength, right? That should have also been apparent from the graph, the pictures that we looked at earlier. As we increase the frequency, you would notice that the wavelength got shorter and shorter. And when we lower the frequency, the wavelength was getting longer and longer. It's because of this inverse relationship. So let's go straight to the question pool questions. What is the formula for converting frequency to approximate wavelength in meters? We just looked at the formula, and the answer is that wavelength in meters is equal to 300 divided by the frequency in megahertz. Again, that is just writing out this formula here. They just write it out. Instead of using the equal sign as a formula, they just write it out and describe the formula. So once you learn the formula that wavelength is equal to 300 divided by frequency, you will have no difficulty. Again, we do use the lambda, the symbol lambda, the Greek letter lambda, to represent wavelength. So on the slide that I would have showed you earlier, that symbol was called lambda, if I did not mention it before, right? So let's go to the other question. How does wavelength of a radio wave relate to its frequency? Well, we made the point a little earlier, and it's apparent from the graphic that we saw that as the wavelength gets shorter, the frequency increases, which is the answer, right? Okay, so in amateur radio speak, sometimes if you hear an amateur radio person talk, they will say, okay, I'm going to use the 2 meter frequency. So persons who are already in radio, React members, for instance, you might hear someone in the amateur radio will say, okay, I'm going on 2 meters. But you say, but wait a minute, you're going on 2 meters? How is that a frequency? Well, it's not a frequency, it's the wavelength that's associated with the frequency. So radio operators, hams, we tend to use, instead of saying we're going on the 144 megahertz band or 144 to 148 megahertz band, instead of giving the frequency, we give the wavelength. And that is perfectly fine because we know that there's a relationship between frequency and wavelength. So it's just another way of representing the frequency. You just say the wavelength that you're using, right? Because of that relationship. So they make the point here that sometimes you use the frequency. When we're talking about frequency, we use the wavelength, all right? So anytime you want to find out what frequency or wavelength, you use this formula or the previous one. So let's go to the question in the question pool. What property of radio waves is often used to identify the different frequency bands? The answer is, of course, the wavelength or the approximate wavelength. So we just talked about the 2 meter amateur radio band. So when we talk about the 2 meter amateur radio band, we are talking about the frequency between 144 and 148 megahertz. But how do we actually work that out, or how do we get that, right? How do we know that the 2 meter band is the 144 to 148 megahertz band, right? So if you think about it, 2 meters, what would be the frequency related to 2 meters? Remember we said the formula is that the wavelength is equal to 300 over the frequency. So if we wanted to find out in meters, what is the frequency for 2 meters or vice versa? We could use this formula here and say, all right, we know that the wavelength is 2 meters. And we want to find out the frequency associated with the 2 meters. So let's use this formula here. So we have the frequency, we want the frequency, but we have the wavelength. And we know the wavelength is 2 meters, so we are in the 2 meter band. So if we divide 300 by 2, or 2 into 300, that is 150, right? And 150 is approximately the 144 to 148 amateur radio band. This is the spectrum that amateurs, when you get your license, you will see that you have permission to use this part of the spectrum. All right, so that's why we say approximate, right? And if you were to divide 148 into 300, you'll get 2.03 meters. So that's why we say the 2 meter band is the 144 to 148 megahertz band, because the 2 meter band, or 2 into 300, is 150, which is approximately 144 to 148. So that's the relationship. So we talked about this other point a little earlier. We said that the entire range of radio frequencies are categorized. We talked about high frequency, or HF. We talked about very high frequency, or VHF. And we talked about ultra high frequency, or UHF. And if you may recall that HF is 3 to 30 megahertz. All right, if you recall. And then you may recall that VHF is 30 megahertz to 300 megahertz. And then you may recall that UHF is 300 megahertz to 3000 megahertz, or 3 gigahertz from the chart we looked at a little earlier. That's why we did those charts, right? Because they don't have that material in the study guide here. So I just thought we'll present it to you visually up front as a poster afterwards. So let's go straight to the questions in the question pool. They're asking us, what frequency range is referred to as HF? So by definition, that's why we need to learn what is HF, VHF, and UHF. HF is 3 to 30. So the distractor questions, they will try to tell you 30 to 300, but you know that's not HF, you know that's VHF. They might tell you 300 megahertz to 3 gigahertz, but you know that is UHF. So the correct answer for what frequency range is HF? 3 to 30 megahertz. So you need to learn that table. Again, remember the magic number 3. They come and ask us now, well, what are the frequency limits? So you see how they're mixing up the question? This question here, they say, what is the frequency range? They come and ask us now, what's the frequency limits? Just another way of asking the same question. What are the frequency limits? But this time, they're asking us for the VHF band or the VHF spectrum. It's not 3 to 30 because 3 to 30 is HF. It's not 300 to 3000 megahertz because that is UHF. We know that VHF is between 30 and 300 megahertz. So you could have probably predicted now what the other question was going to be. What are the frequency limits for the UHF spectrum? And look what they do here, right? It's not 3 to 30, it's not 30 to 300, but UHF is 300 to 3000 megahertz, or 300 megahertz to 3 gigahertz. All right. So radio frequency or radio signal is sometimes abbreviated as RF. And the RF simply means radio frequency. So we are doing an amateur radio course and we are talking about frequency. So we typically refer to radio frequency as RF. You know, somebody will say, okay, the signal is RF. What do they mean? It just means that the signal is a radio frequency signal. Let's go to the question in the question pool. What does the abbreviation RF refer to? The correct answer, radio frequency. And they embellish it by telling you signals of all types. So it's radio frequency, signals of all types. That's what RF means. So anytime you hear someone talk about RF, they're talking about radio frequency. So let's continue. So as amateur radio operators, we need to know what frequency to use when we need to communicate. In other words, we need to use the right frequency. And you saw earlier, we have different types of frequencies we have access to as amateur radio operators. We could operate HF, which is between 3 and 30 megahertz. We could operate VHF, which is between 30 megahertz and 300 megahertz. And we could even operate UHF, which is between 300 megahertz and 3000 megahertz or 3 gigahertz. And as amateurs, we have spectrum even higher than 3 gigahertz, yes? So, but we need to know when we need to communicate what frequency to use because each of those frequencies behave differently. HF properties are different to VHF to UHF. And because they're different, we need to know which to use when we need to communicate. So if I want to communicate locally here between San Fernando and Point Fortin, or between Port of Spain and Chaguanas, or between Arima and Sangre Grande, or between Diego Martin and Caranage, versus I need to communicate between Trinidad and Puerto Rico, or between Trinidad and South Africa, or between China and Australia. We have to use different frequencies because each of them propagate or operate differently, all right? So they are making the point here that VHF and UHF frequencies are generally line of sight, right? That means when you transmit either VHF or UHF, it leaves your transmitter and goes in a straight line outwards. So therefore, we tend to use VHF and UHF for local communications, tend to, right? So once we are talking locally, we will probably be using VHF or UHF frequencies, right? So let's go straight to the question in the question pool. Why are direct UHF signals rarely heard from stations outside of your local coverage area? Right? So remember we dealt with a diagram a little earlier where we showed you that VHF and UHF signals go straight and they do not, they go straight through the ionosphere. It doesn't bounce, so it doesn't travel very far. Well, that's where that concept comes in. And the answer that they give us here is that UHF signals are not usually reflected by the ionosphere. So if you recall that diagram, we show that VHF and UHF go straight through the ionosphere. That's why we put that diagram up, to show you that HF is the signal that will bounce off the ionosphere and go to another part of the Earth. Whereas VHF and UHF signals will go straight through the ionosphere out into space. And that's why it doesn't go any further than local communications, all right? Also, they are making the point that because UHF and VHF signals are line of sight, it will be blocked by the curvature of the Earth. But notice we said that unlike light, the radio signal will travel just a little further and will be refracted, all right? So just bear that in mind. Even though it's line of sight, it goes a little further than what we know to be actual visual line of sight. So it goes a little beyond visual line of sight due to the curvature of the Earth. So let's go straight to the pool question that deals with that. Why do VHF and UHF signals usually travel somewhat farther than the visual line of sight distance between two stations? Well, we just talked about it, and we also looked at a diagram earlier. The answer is the Earth seems less curved to radio signals than to light, all right? Because the radio signals will hug the Earth's curvature a little bit, as opposed to light will go straight. It will typically not diffract in the same way or refract in the same way. So let's talk about a problem associated with VHF and UHF frequencies. There's a concept called multipath distortion. So imagine you are transmitting a radio signal and it leaves you and it gets to your destination. But sometimes signals can arrive at that destination through different paths. It could go straight, but it might actually bounce off a very large water tank on a hill and arrive at your destination. But that signal will be delayed compared to the first signal. So when that happens to a radio signal, when the main signal reaches straight away and 2 or 3 or more signals might reach via some sort of other path, they call that multipath. And you can have that signal distorted because imagine, remember just now, a little while ago, I had a little bit of interference because you heard an echo and that was a bit of distortion. In the same way, if you have signals that arrive and then a similar signal arrive a little later on, then you can get distortion. So that's the point that they're making here, that multipath distortion occurs when your signal arrives at a station or receiving station using 2 or more pathways. And that is entirely possible with radio waves because they not only will go straight from your transmitter to the receiver, they may bounce off other objects. And a large water tank on a hill, for instance, is a good example of how a signal will bounce off an object and result in multipath. And they make the point here, when the signals arrive, they may be going through different lengths. And as a result, they may arrive at the receiver out of phase and they might cancel one another. So just bear that in mind, that signals leaving a transmitter may arrive using different pathways and cause multipath distortion or cancellation of the signal when it comes via different pathways. So the question in the question pool. What should you do if another operator reports that your station's 2-meter signal, right, that's VHF, 2-meter signal was strong just a moment ago, but now they are weak or distorted? So let's look at some key words in this question. 2-meter, right? And we recall from earlier that 2 meters is in the VHF part of the spectrum. So we're not talking HF and we're not talking UHF, but we're talking VHF. So the properties associated with VHF signals is important here. when they were strong just a moment ago, but they are now weak or distorted. So once you hear distorted, you're thinking, well, you know what? That may be as a result of multipath or reflections, right? The signal may have arrived at the receiver in multiple paths, right? So let's see what the correct answer is. To solve that problem, try moving a few feet or changing the direction of your antenna, if possible, as reflections may be causing multipath distortion. So those of us who are accustomed to using radio, you know, sometimes we come across distorted and you may hear a net control operator or the other radio operator say, could you move or shift a little bit? And then you take 2 or 3 steps. If you're in your yard, you make 2 or 3 steps forward or backwards or to the side. And then when you move, the person tells you, yes, your signal now is loud and clear. And you're wondering, well, how come? Well, it could be as a result of multipath distortion that was resulted in your signal from being distorted, right? Okay. And they just re-emphasize that point that moving just a few feet might eliminate or reduce the effects of random reflections that are causing multipath distortion. So they tell us here that multipath distortion could affect both voice and digital transmissions. What they mean here is that as amateur radio operators, we do not only communicate using voice. Voice means that we are talking, speaking into a microphone, goes through the radio, goes to the radio signal, arrives at the receiver. That signal is interpreted by the radio, and then your voice comes through the speaker. So that is voice. But amateurs do not only communicate using voice. We also do digital transmissions. What that means is that we can connect a computer to a radio and send a signal like an email. We can send an email, or we could send some other, we could send a picture. We can send text messages. But the point is that those are digital transmissions as opposed to voice transmissions. You can even use a radio alone and send a digital transmission. But typically hams connect computers to radio to send signals. Those would be digital transmissions as opposed to voice transmission. And they're just making the point here that multipath distortion could affect both. Let's deal with the question pool. What may occur if data signals arrive via multipaths? So you already know, once you hear multipath, you're thinking, all right, signal is reaching one way, then another way, and what happens there? It might cancel out, it might cause distortion, right? But they're saying data signals. They didn't say voice signals. If it were voice, the person would sound distorted, but if it's data signals, or if it's digital transmissions, remember we said a ham could use a computer and send a text message or a picture or an email? Well, those are data signals. So the answer to this question is in relation to data transmission, not voice. So let's see what the answer is. The answer is error rates are likely to increase. The error rates that they're talking about is with respect to the data signal. You might have garbled information when you look at the computer output, or it may be obfuscated, or it may be obliterated, or it may be canceled out. You may not see any useful information coming out. So that's what they mean by error rates. And the error rate has to do with the digital signal or the digital transmission. All right, let's see what else we can cover before we come to the end of today's session. They tell us as amateur radio operators, knowing how VHF and UHF signals move or propagate can help us communicate even in adverse conditions. And that's what, as amateur radio operators, we are aiming to achieve. We want to know, how do we communicate in adverse conditions when there's an emergency, for example? How do we do that? And knowing how the signals move around or how they propagate is the word you will hear a lot. Propagation, how does the radio signal propagate from one place to another? When you transmit it from a source or a transmitter and it goes to the receiver, we say that that signal is propagating through free space or propagating towards the receiver. They tell us when we're using a repeater, you might find yourself where a direct path is not possible. And that's why we looked at the diagram a little earlier about the difference between simplex or radio to radio versus repeater operation. So they're telling us when we're trying to use a repeater, you may find that you cannot get through to the repeater. What can we do in this case? They tell us that we could try using a directional antenna and bounce it off of a building or other obstruction. So that's another way that as hams, we can get our signal. Our signal cannot get to the repeater or to the other side directly. So we have ways, we are trained. They say, hey, we can use a directional antenna and bounce it off. Matter of fact, hams do a lot of bouncing. You might have heard of amateur radio doing moon bounce. So amateur radio operators do bounce signals off of the moon and hit that signal to the opposite side or the other side of the earth. So as hams, we can use directional antennas and bounce signals off buildings or other obstructions. Earlier, I talked about a large water tank. If I have a large water tank at the top of a hill, I could point my antenna and try to bounce my signal off of that and to hit a repeater that I might not otherwise hit. If I am in Port of Spain and I cannot get a repeater in the central range of Trinidad, I could use my antenna and try to point it at a big water tank on Laventil Hill. It might be a metal water tank and it might cause my signal to bounce off there and get to the repeater in the central range. So those are things that hams will do. So let's go to a couple of quick questions to end off our session. Let's try and finish this section here and we will end today. Okay, the question. When using a directional antenna, how might your station be able to access a distant repeater if buildings or obstructions are blocking the direct line of sight path? Well, we just discussed that concept. We will try to find a path that reflects the signal to the repeater. Remember my example, I tell you if I'm in Port of Spain and I can get through to the repeater located in central range of Trinidad, I could try and bounce my signal off our water tank in Laventil, on the Laventil Hills, right? So that's what I'm doing. I'm trying to find a path that will reflect my signal to get to the repeater. And those of us who are reactors with React radios might understand some of the times when we try to do these things. They say, oh, that's what they're doing. They're trying to bounce the signal off another object. So we talked about this concept of knife edge diffraction via the diagrams a little earlier. So let's go straight to the question pool question on it. Which of the following effects might cause radio signals to be heard despite obstructions between the transmitting and receiving stations? Remember that diagram where we saw that there was a hill with two very sharp peaks and the signal kind of curved around it or moved around it and the signal got to a place where it would not have gotten otherwise? Right. So that is called knife edge diffraction, where your signal could get to a place that we would not otherwise do. But because of those very sharp objects or those very sharp edges of buildings or mountains or tanks or anything that's very sharp, the signal will be diffracted and could drop into an area that the signal would not have otherwise gone. So mobile operation, which is when you have a radio and you are moving around. It could be that you're in a car, for instance, driving around, which is the typical example of mobile operation. So you could think of mobile operation as being in a car, all right? You can think of it that way. But you could also be walking around and that is mobile operation. You're just not in a motorized vehicle, all right? So when you walk around or you move around and drive around in a car, your antenna is moving and you might be talking to someone. That means your signal will be constantly varying or changing as you are driving around. And when that happens, because your signal is varying as you move, it's not as steady as if you were stationary at a base or staying in one location. You're moving around, your signal will also be changing and shifting relative to the person receiving your signal, all right? What happens is that the signal varies and sometimes you will hear a chip, 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 chip sort of signal that comes along with your audio. And that is called picket fencing. It's a sort of fluttering sound that occurs when you move. So if you're a reactor or have you ever used a radio in analog mode and you hear that sort of fluttering chatter sort of thing, well, what that simply means is that you, yes, good point, Anthony. I just noticed your point here. Oh, Lisa, sorry, I'm just seeing some of your comments. My apologies, folks. I'm now seeing that we asked what page we are on. If it's the PDF that you're looking at, it's page 33 that we are on now. And on the actual document, it's page 28. So it says 28 on the document, but on the PDF, it's page 33 of 99. So whichever, if you're looking at the printed document, page 28, if you are viewing PDF, page 33. Sorry about Lisa. Took me, wasn't quite paying attention to the chat box. Yes, Eric, thank you very much for your comment as well. And Anthony, good point that you're making. Yes, you're correct. That water tank that we're talking about, we said it should be a metallic water tank. So it should be a metallic object that you're looking to bounce off, right? So yes, bear that in mind. We generally talking about metallic objects. However, sometimes when it comes to knife edge diffraction, it may not necessarily be a metallic object, right? But for certainly bouncing off of objects, yes, it typically will be a metallic object, all right? Typically, all right? So good point indeed. Yes, indeed. All right. Right, so we were talking about the term picket fencing, right? Let's go straight to the question in the question pool. What term is commonly used to describe the rapid fluttering sound sometimes heard from mobile stations that are moving while transmitting? So if you're a reactor and you have used a radio and you hear that sort of fluttering chip, 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 chip sound, sometimes you may hear the term, radio operator may give a signal report to another one and say, your audio is loud, but your signal is sounding as though it's picket fencing, right? So you're hearing the person, but just in between, you're hearing that fluttering sound. So you're hearing them, but that bit of interference that you're hearing, you can describe that as picket fencing. And it's as a result of you moving or your station being mobile and you're moving while you're transmitting. Another condition that could impede your transmission, especially on UHF and VHF signals, is vegetation, meaning trees or bush, trees of any sort, because they have sap in it, right? They affect the radio signals. Sap has moisture. So if you have a lot of tall trees and you're in the forest and you're operating on VHF and UHF, your signals will be affected by those trees, all right? So, right, so Anthony, I just saw that you asked the question about whether it must be metallic. Well, the answer is yes, but just bear in mind that radio signals can also be affected by non-metallic objects as well, right? But typically, yes. I mean, you're looking for a metallic object to bounce off, or it could be a hill, and the hill could have metallic properties in it, right? But not strictly, right? So for instance, we do moon bounce. I don't know if we will say that the moon is a metallic object, but it may have metallic properties. The point is that it's a solid object, and it will certainly bounce signals off of. But good question that you're asking. Yes, we typically refer to metallic objects when we are talking about reflecting or bouncing off or refracting and so on. But it's not only metallic objects that factor in when we are talking about the way propagation works, all right? So for example, knife edge, for instance, arguably it just needs to be a sharp object, right? Sharp objects, right? And if it's metallic, well, even more so. So let's get to this question again about vegetation. They're telling us here that VHF and UHF signals are affected by vegetation, and they use the term impede the transmission, right? So that means it reduces your signal. So if you're in the forest and you have trees around, just note that those very tall trees, all that bush will affect your signal. It will impede your transmitter. So they're making the point here, keep your antennas out of trees or keep them above trees. Let's go to the question in the question pool. And when we have completed this question, we will end there for today because we have exhausted our time. We have gone a little bit over by a couple of minutes. Okay, so let's look at, well, Andrew is asking, is HF affected by trees? And the answer will certainly be yes, because SAP in trees do affect radio transmission. But the point I think they are making here is that UHF and VHF frequencies are very much affected, or heavily affected by the vegetation. When we come to other radio properties later on and we look at sky wave and ground wave, you will realize why they might be telling us maybe not so much on HF, right? So yes, it will affect the signal, but it might affect more the ground wave, but it would not affect the sky wave, right? So very good question, Anthony. We will discuss a little bit more about that a little later on in the course as to HF signals, right? The point that they're making here in this question, why might the range of VHF and UHF signals be greater in the winter? So notice that this is an American exam, right, that we're looking after. So they're talking about winter. So they're kind of asking a round the road question. Why might the range of VHF and UHF signals be greater in the winter? But look at the answer that they're saying. Less absorption by vegetation. You know, in the winter, a lot of the trees drop their leaves and so on, right? So that's what they're trying to say, that the vegetation cover is less during winter. Right? A very tricky question that they're asking here. But the point that is made and the theory that you are learning is that vegetation definitely affects radio signals and particularly VHF and UHF signals. All right, so thank you very much for the question. Right, so Colin, very good point that you're making here. Yes, hills do contain metallic content such as iron ore. So very, very well, very good point that you're making there, yes. All right, so hills do contain iron ore and other metallic deposits, or it can contain those metallic components, and therefore will and can affect signals in different ways, all right? So folks, thank you for going a couple of minutes over time on today's session. I think we made some good progress. Let's continue. We want to encourage everyone to read the material, read ahead, take a look at the question pool. We gave you some links at the first session where you can do practice exams. So you can start doing practice exams all now. See how you're doing, what you recall. You can review the videos from the previous sessions if anything is unclear. You can send an email to me at the email address on the first page of the slides if you have any questions, and we will address those questions at the start of the following class. Our next session will be held on Friday, the 10th of July. You will get an email with the link to that session. So persons on the class, you can expect to receive at least one email from me per week. So we'd like to encourage everyone to continue to be safe and do have a great weekend all. Thank you so much and all the best. Bye everyone.